get us on to the next speaker, who is Salil Vadhan. He has come all the way down Mass Ave from that other school. And he is the Vicki Joseph Professor of Computer Science and Applied Mathematics at Harvard, as I mentioned, in the School of Engineering and Applied Sciences. And he's a CSAIL alum. So with that, I'll hand it over.
Thank you, Renee. Works. My laptop's connected? Yep. Great. All right, hello everyone. It's an honor to be here. I was a graduate student, not in CSAIL, but the predecessor, Lab for Computer Science, in the late 1990s. I think this photo was taken at one of the corn fests that Tom used to organize every fall for the theory group. A great way to build community and welcome the new people in the group. I'm hidden there in the back, and as Maya said this morning, the hair. I had hair back then, and I'm standing behind Danny Lewin, who Tom talked about, co-founder of Akamai. I was lucky to be in Danny's cohort and lucky to have Danny as a friend and research collaborator before Akamai consumed all of his attention. In addition to being brilliant, Danny was an extremely warm and kind person, and also incredibly strong physically. We're in the process of moving homes right now, and I can't help but remember when Danny helped us move back then in the late 90s, and things that would normally take two people to carry, he would easily just lift up and with a big smile carry on one shoulder. So in addition to really what was an amazing group of the theory group at that time was incredible in terms of its intellectual energy, but also the culture among the students and postdocs was extremely collaborative and supportive and fun-loving, not really a sense of competitiveness at all. A really remarkable time. And we were also blessed to have an extremely inspiring and broad, of course, star-studded set of faculty to learn from. There's Tom, and here in the center is my amazing PhD advisor, Shafi Goldwasser. And one of the things that permeated the theory group at the time was really the interconnectedness of theoretical computer science. How insights from one subfield of theoretical computer science led, when applied to problems that seemed completely unrelated in another field, led to some of the most remarkable advances and breakthroughs in our field. And one prototypical example that really exemplifies this was just as one vignette, the story of zero-knowledge proofs that were introduced by Shafi together with Silvio Micali and Charlie Rakoff in the mid-1980s to tackle problems in cryptography. How could one party convince another of something without revealing their secret information? This concept of zero-knowledge proofs, it had first impact on distributed computing, showing amazing feasibility results for the design of fault-tolerant protocols through work of Silvio Micali, Oded Goldreich, who was one of my mentors was visiting faculty in LCS at the time, particularly when you want to deal with when the processors that are faulty are behaving in an adversarial or Byzantine manner. It also introduced a new concept, way of thinking about mathematical proofs to complexity theory, introducing randomness and interaction to proofs. And this concept of probabilistic proofs completely changed our way of thinking about classical complexity classes like NP that we're all familiar with from the famous P versus NP question, which in turn then, through another amazing connection established by Shafi and her collaborators, impacted questions that algorithms researchers like Michel Goemans and optimization researchers had been thinking about for years, about when you have an optimization problem that's hard to solve exactly, is it feasible to efficiently find approximate solutions to those optimization problems? And that in turn, going back to what Ankur mentioned this morning, many things in learning are hard. So this enabled understanding the hardness of agnostic learning problems, and also led through breakthroughs in coding theory through work by people like Madhu Sudan in list decodable codes. So this feeling that it was a really special time in the theory group wasn't just felt by students, but this is an email discussion with Shafi when we were talking about the possibility of early graduation. And she said one downside if you graduate early is MIT is a truly remarkable place to be right now. Of course, it's partly due to the group of students around. So it really was a special time. Shafi helped me find a best of both worlds solution where I did graduate, but I stayed in MIT one more year as a postdoc, continued benefiting from this amazing environment before going on to be a postdoc at the Institute for Advanced Study for a year, and then joining the computer science faculty down the road at Harvard, where I continued to work at the interface of two different areas of theoretical computer science, complexity theory and cryptography, studying the complexity theory of zero-knowledge proofs, as well as problems in pseudo-randomness and de-randomization. And then in 2007-8, it was my first sabbatical. I was really looking for something new to get into. And what caught my eye was the emerging new field of research on differential privacy, invented by Dwork, McSherry, Neeson, and Smith. Smith, another CSAIL alum who overlapped with me by one year. And differential privacy aimed to address the problem of how can we open up sensitive data sets with sensitive information about people for sharing and statistical analysis for societal benefits, while providing strong privacy protections to the individuals whose data is in those data sets. And in particular, differential privacy aimed to, I find it better when I can look at this screen, aimed to provide very strong privacy protections that hold regardless of what kind of an attack strategy a potential attacker might employ, and whatever background information, other data sets they might bring to bear in trying to attack the release. And the reason the differential privacy was needed is that it was increasingly becoming understood that the traditional methods for protecting privacy in sensitive data sets, such as de-identification and coarsening, were typically ineffective and subject to often very severe privacy attacks like re-identification, reconstruction attacks, and membership inference attacks. To give you a taste of how, just a very quick taste of how differential privacy is achieved, consider, when you have a sensitive data set and you just want to even answer a basic question like, what proportion of the population has some characteristics, like has a certain blood type and a certain disease status? Well, one way to achieve that with differential privacy is just to compute the actual answer to that statistic and add a small amount of random noise. And the point is that as the population size, n, grows, the amount of noise that you need to hide the effect of each individual data subject vanishes. And so you can still allow signal about the population to come through while providing very strong guarantees of privacy. And then this is just a very simple example of one extremely simple statistic. But what differential privacy does is quantify what we mean by privacy and allow you to quantitatively reason about how much more complex methods for carrying out analyses on data, with many queries, training machine learning models, and so on, how privacy loss accumulates and can be controlled in such data releases. So when I was starting to work on differential privacy, there was this beautiful result that had just come out by Blum, Liggett, and Roth, saying not only can we release statistics with these strong protections of differential privacy, we can even do synthetic data generation, which I think Daniela mentioned maybe in the opening remarks this morning, where we don't release statistics, we publish a data set that looks like the original data set, but has these strong privacy protections where no individual in the original data set has any noticeable effect on what you publish, yet preserves a huge amount of statistical information about that data. The remarkable thing shown by Blum, Liggett, and Roth is that you can actually preserve even an exponential number of statistics about the original data set with this strong protections of differential privacy. In particular, if my number of attributes is smaller than my number of observations or data subjects, then even the exponential in D here, the exponential in D number of possible combinations of attributes, the proportion of the population that has any such combination will be approximately preserved in the synthetic data set that you publish. So this seemed like a great, almost a holy grail of research on differential privacy. The problem is that their algorithm is extremely inefficient. The amount of computation time grows exponentially with the number of attributes in the original data, and so is infeasible, completely infeasible for most practical data sets of interest. So this was my entry point into differential privacy, and our first set of results were bringing tools from complexity theory and cryptography to understand whether this exponential complexity was really inherent or could somehow be avoided with more clever algorithm design. And we showed that it indeed is inherent, that if you want synthetic data generation with these strong properties of, that Blum, Liggett, and Roth achieved, any algorithm that you have for producing the synthetic data set will, in the worst case, either require exponential time or, in some cases, fail to provide the utility, the statistical accuracy guarantees that it promises. And so this was just the starting point for a long body of work with my group on one by one going through many of the sort of foundational questions in differential privacy and bringing the full theoretical computer science toolkit to bear from many different areas of theoretical computer science to understand what are the fundamental limits of differential privacy. So we started out, as I said, with synthetic data generation. Then we asked if you don't need to publish a synthetic data set, but you just want to be able to answer many complex queries, what are the limits to doing that in a computationally efficient way? What if you want to just release many very basic, simple statistics, like the means of all of the attributes in your data set, or approximations to the cumulative distribution functions of continuous variables? What if you want to do, as Raluca mentioned this morning, do differential privacy in some federated context where you have data that might be partitioned between two different hospitals? Are there additional limits that setting introduces? And what about kind of the complexities of optimally budgeting your privacy loss as you're releasing many statistics? And we brought in tools from complexity theory, cryptography, learning theory, combinatorics, and algorithms to try to tackle these questions, all drawing this interconnectedness of theoretical computer science that was ingrained in me as a student here in CSAIL. In addition to doing this theoretical work, about a decade ago, we also launched a large interdisciplinary research project on data privacy, the Privacy Tools Project, where we collaborated with law scholars to understand the relationship between the mathematical ways we had of thinking about privacy with their kind of normative and legal perspectives on privacy, as well as work with researchers in quantitative social science and statistics to understand how the methods we were developing met, or there were gaps that needed to be bridged with their needs as practicing researchers working with sensitive data sets and trying to share those data sets in a safe way. And all of this work that we were doing, as well as foundational work done by other groups around the world, set the stage for a really remarkably fast transition from theory to practice for differential privacy, with now quite a few large-scale deployments. One of the highlights being the US Census Bureau committing to releasing all the public use data products from the 2020 decennial census protected with differential privacy, as well as deployments by essentially all of the large tech companies and a really exploding industry of startups and consulting companies and enterprise software offerings in differential privacy. We also, so one compelling example of the kind of data for good applications that I like to see and we want to support happening in this space was how Google and Facebook during the pandemic released mobility data sets protected with differential privacy for epidemiologists and policymakers to understand the impact of interventions like lockdowns on people's behavior. So to support uses like this, we, in the last few years, I'm co-leading an open source, community-driven open source software project, OpenDP, to have this really engage the whole community in developing trustworthy open source software for differential privacy that can be deployed safely by custodians of sensitive data who don't have the resources of the Census Bureau or big tech companies, or to be able to hire a consulting service to find tools that they can apply to make effective use of this new technology. So if you have any interest in this space, do join our community, and I'd be happy to talk with you more about it during the reception. And so with that, let me conclude with a huge thanks to Shafi, the full theory of computing community here at MIT, the faculty, the students, the postdocs, the wonderful staff, the math department, where I was a graduate student, CSAIL, and MIT for giving us such a memorable, rewarding, and life-shaping experience here. Thank you.